When looking at coordinates in a finite geometry, then you look at level surfaces of a function. And level surfaces of a function appear in geometry all the time. All measurements are based on measuring distances. And this process produces use level surfaces. For example, what Descartes did is he introduced coordinates like the x-coordinate, the y-coordinate, and that defines you a point. And if you look at these two functions, these are two level surfaces which you intersect. Now, if you do that in the discrete, there's something strange happening. So if you take, for example, f equal to c, that's kind of something natural. You just look at all the simplices where f minus c changes sign, but then you start looking at the second function g, and then it starts to matter whether you take f equal to 0 or g equal to f equal to 0 or minus f equal to 0, or if you switch f equal to 0, g equal to 0 to g equal to 0, f equal to 0. So there's no way we can kind of get this fundamental commutativity of coordinates saved in the discrete. Let me just say, I mean, about non-commutative space, there are many, many different places where non-commutativity comes in. The most prominent example is noncommutative geometry, which is a very general thing. What you take, you replace geometry by a function space. For example, a topological space you replace by a space of continuous functions. It's an algebra, and then you have a C-star algebra. C-star algebra can then be generalized to non-commutative cases. Also, when you look at probability theory has a non-commutative generalization. You just look at probability theory first as a, commutative for Neumann algebra story, and then you go to non-commutative for Neumann algebras. I used this myself when I was working on the entropy problem for the standard map. The entropy problem of the standard map is actually just a problem finding the determinant of some operator, some element in a von Neumann algebra, which is a cross product of L infinity of the space with the dynamical system. So very, very prominent is here the non-commutative torus, where you just take the circle and you take a translation by an irrational rotation, and then you get the nice non-commutative algebra, and this is called the non-commutative torus. And then you can look at spectral problems like the almost Mathieu operator, and look at the Lyapunov exponent. Actually, kind of that's the reason why I was interested in this whole thing when I was a grad student. So this is kind of non-commutative geometry is probably the most natural way to get from a commutative setup to a non-commutative setup. You just replace commutative algebra by non-commutative algebra. So that's the story. But it's interesting, for example, when you look at already very interesting when you look at Riemannian geometry, where you cannot just do it with the algebra or a Hilbert space itself. You need also an operator. And this is the spectral triple of Ghon. And I'm very fond of the Dirac operator, because if you look at the finite space and you look at the Dirac operator on it, then you essentially have what is a delta set. So you have a topos, a finite topos with a geometry, and you can do a lot of geometry with this kind of philosophy of looking at the Dirac operator as your basic thing, because the Dirac operator defines exterior derivatives, defines you geometry, like you curl, diff grad curl, defines you calculus. All we do in calculus can be understood using the notion of derivative, and then the integration. And there has to also be here, it has to be there's an integration, which is usually just a trace, a type of trace. And that's kind of the integration here. You have in spectral theory, that's how I got into that. I wanted to solve the spectral problem here to find the entropy. That is a spectral problem, and used essentially anything I could get hands on. And one of the things where Lyapunov exponents appear is in spectral theory of random operators. Another place where a non-commutativity comes in was in something I did in 2006, which is kind of an interesting story. I asked myself, if you have a metric group xt plus with the translations are in this group, if you add an element, that should be preserving the metric. And so we say this is natural if you apply the forgetful functor to the metric group, and you just have the metric space if this determines the algebra up to isometry. So I wrote about that in 2021, and the point is that the integers are not natural. So you have another group structure on the integers, which is non-abelian and so not isomorphic. And this is the dihedral group, the infinite dihedral group. It's a reflection group, and this reflection group is also, this is the natural. You can define a metric space so that the group comes in. And this is also very I think very old. If you look at the geometry approach of Euclid to geometry, you don't look only at the points, and you look also at translations. You look at groups, like the group of translations, the group of rotations, the group of reflections. So what you can do is all these groups you can also understand using reflection geometry. The group of translations has a cover, kind of a Coxeter cover by reflections. You take the points on our reflections. Instead of points, you look at reflections at points, which is now you have a group which is non-abelian, reflection at this multiplied with a reflection at here is a translation. So translations are kind of a subgroup, but the group itself is non-abelian, and this Euclid would have kind of, if you take translations and rotations and translations, that's already a non-commutative group. It's kind of also in the spirit of Klein's Erlanger program. You don't look at the object geometry itself, but you look at the automorphisms. A third place where non-commutativity comes in is if you look at a space which is not flat. It's what Gauss probably first kind of really studied seriously. I mean, one knew non-flat geometries before, but one was always focused on this parallel axiom, Euclid, and this is kind of like an emancipation from Euclid, that you look at other geometries, you look at hyperbolic geometries, or you look at sphere geometries, any type of Riemannian manifold. That's Riemann later introduced this Riemannian geometry. Or Gauss already had this beautiful theorem, Gauss-Bonnet theorem. It, kind of makes this local notion of curvature global, relates it with a Euler characteristic, which is a topological notion. So also here, I'm just putting here some things which personally for me are exciting. Also these in finite spaces, there's no problem to have Gauss-Bonnet. It's actually much easier in a graph or simplicial complex to have Gauss. I'm currently interested in functions on a simplicial complex or functions on a graph, and you look at the level sets. So, and the nice thing is that the level sets are almost universally just submanifolds or empty. That's the theorem which we have looked at a couple of times. This discrete Sard theorem is extremely exciting because it gives you from manifolds new manifolds. And but it's related to the notion of coordinates, right? If you have on a two-dimensional space, for example, you give a point, fix a point, and then you maybe take the distance, or you fix maybe the picture of the GPS picture. If you have two satellites, this determines you a hyperboloid of all the points which have the distance between satellite A and the point, and satellite B and the point, where this difference is constant. That's what you can measure. You measure the differences. You don't measure the distance. You can do that by just see how much waves are shifted, right, with respect to each other. So you can get the distance between the point which is a hyperboloid in space, and then when you have three satellites, you have actually then the intersection of two hyperboloids, which is in general just curve, or you still don't have the point, but if you take four GPS satellites, then you have three hyperboloids, which generically just is a finite set of points. With five, then you can fix the location. But it's all based on functions, level surfaces of functions. Any measurement in physics, everything can be measured using level surfaces. But it's very interesting, kind of maybe philosophically, that in the very, very small, maybe if you kind of take the point of view that space is maybe not a continuum, then this is normal commutative. These coordinates are normal commutative. But I should also say there is no indication at all that space is discrete or anything. We have no evidence. There is no measurements which indicate that that we have even on the Planck scale something discrete. Okay, that's what I wanted to say today.